Today's video is on how to find the area between a curve and the x-axis. So one thing about area and integrals is, let's say if we have a graph that hits the x-axis like this, maybe let's say that that's 1 and this is, 5. So if we want the area between the curve and the x-axis, we're looking for this area in here. And if we've got a function f of x, we find that using a definite integral. So from 1 to 5 of f of x. And that result would give us the area that's shaded in blue. Let's say instead I had a curve that looked something like this. So this is our function f of x. If I want to find the area between the curve and the x-axis, one thing I guess I didn't mention with that other example is these points that I'm highlighting are the x-intercepts. And they're important when you're trying to find the area because it's the point where the graph hits that x-axis. So it's essentially going to be the sort of how to find the start and end point of your integral. So in this case, let's say that is 1 and 5 again. We could use the integral to find the area here. So again, I'll write from 1 to 5 of f of x dx. But what it's going to do is give the negative of the area. So it'll give the answer the value of what's under here, but it's going to give it as a negative value instead. So you'll get an answer like something like, I don't know, I'm just making up numbers now, but maybe you might get an answer like negative 30. So that would be, if you're just asked to evaluate the integral, the answer would be negative 30. But if you're asked to find the area, you would just change it to 30 and say that the area is 30. Because when we're talking about area, it doesn't really matter whether it's above or below the x-axis, but this is how the integrals work, that it will always give a value of negative when it's below the x-axis. And let me try to show one more thing before we go over this example. Now let's say we have a graph like this and we want to find the area between that graph and the x-axis. So what's happening is that there's two different areas and that we're going to have to look at them one at a time essentially. So we've got this area down here, we'll call that, let's say, area 1, and then we've got this area up here, which is called area 2. So we're actually going to have to find each area and add them together. Another important thing, again, is the x-intercepts. So we want to know where this graph crosses, so we find the x-intercepts. So those are these points right here. Let me just throw in some numbers. Let's say 1, 3, and 5. So if we're going to use an integral to find the area, we're going to write two separate integrals. So one of them is going to be from 1 to 3 of f of x dx, and that's going to be used to find area 1. And then we're also going to do a separate integral from 3 to 5, and that's going to be used to find area 2. The thing, though, from what I mentioned in the previous example, is area 1 is below the x-axis. So that means when you evaluate the integral, it's actually going to give you a negative value. So we can still go ahead and evaluate this. The answer is going to be negative, and since we're just trying to find the area, we want to make it positive. So we could do that by actually putting a negative in the front, because that tells me, okay, I know this integral is going to give me a negative answer, but I want the area, so I'm going to go ahead and put a negative in front of that, and then essentially you might get something like negative 10, which will give you just a positive answer. Essentially, whatever we get from that first integral, we want to convert it to a positive number, because for this type of question, we want to know what the area is. The negative, integral-wise, is really just telling us that it's an area that falls below the x-axis. And for the second one, we don't have to do anything like that. If we evaluate the integral from 3 to 5, it's going to give us a positive value, and it's going to be equivalent to that value of, or the area 2 for this example. Now let's look at the example that we're given. So if you want, you could graph the function to get an idea of what it will look like. This is going to be a parabola that's facing downwards, but you can actually solve this problem without graphing it, and I think that's what I'll do as a start for this one. And when you're not graphing though, even if you are graphing or not graphing, what you do need to find are the x-intercepts. So that is when the function is equal to 0. So we're going to solve 50 minus 2x squared is equal to 0. And when I do that, I get two values. I get positive 5 and negative 5. If I wrote these as ordered pairs, that would mean on my graph I have the point 5, 0, and negative 5 zeros are our x-intercepts. So this is the place where the graph can change from positive to negative. And so what we would do is we're just going to compare this with our actual interval that we're given, because we're trying to find the area, in this case, between 0 and 7. If we put those together, think about this as a number line here. We're going from 0 to 7, but what I'm checking with the intercepts is I'm basically checking, can I write an integral from 0 to 7, or do I need to split it up? Because at some point it crosses the x-axis here. So it does cross the axis at negative 5, 0, but that doesn't really matter because negative 5 is outside of that range 0 to 7, or the domain of 0 to 7. But 5 does fall in there. So I'm going to put this extra number of 5. So if we had the graph in front of us, we would know between 0 and 5 is the graph positive or negative, between 5 and 7 is the graph positive or negative. It doesn't necessarily matter, but what this does tell us is how to set up our integrals. So to find the area between 0 and 7, I'm going to split it up between 0 and 5 of our function. I'll fill in the function in a second. And then we want from 5 to 7 of our function. Without the graph, you really just don't know which one's going to be positive and which one's going to be negative, but I know that one of them will likely be positive and the other one is negative, and I know the value that I get that's negative, I'll change it to positive to find the answer for this question. Before we go any further, let's just take a look at the graph. So I graphed this in Desmos, which it is a downward facing parabola. And I also restricted the values to only be between x is 0 and 7. So you can see we confirm here that it does in fact have an x-intercept at 5. And in terms of our integrals, the integral, this is telling us the integral from 0 to 5 is going to give us a positive value. And that's going to give us the area here. And then the integral from 5 to 7 is going to be negative. And that's the area in this region right here. So I'll call this area 1 and area 2. So area 2 here, well, I shouldn't say area, but the value from the integral is going to be negative, and then we're just going to convert it to positive. And then our final area is just adding the two positive values together. Now let's evaluate these integrals. So I'll do these both kind of at the same time because the actual integration is going to be the same. So to integrate 50, that's going to be 50x. And negative 2x squared, I'm going to write it as negative 2. And then the rule for x cubed, I'm sorry, thinking ahead here, x squared, the integral is x cubed over 3. And then the same thing over here. If it were an indefinite integral, I would just put plus c at the end of it, but since we're doing a definite integral, what I do instead is the notation at the end here, this line, and it's just reminding me to plug in 5 and then subtracting, plugging in 0. And over here, I'll write 7 to 5. So again, I'm going to do these both at the same time here. So let me evaluate the top number first. So I get 50 times 5 minus 2/3 times 5 cubed here. And then I'm kind of doing both of these at the same time. You might just want to do one at a time, and that's fine. One thing to be careful of, you'll notice here, I tried to put that whole thing in parentheses. Just going back to just common arithmetic algebraic issues is really subtraction. So that comes into play with definite integrals as well, because you're subtracting that entire second piece, and you want to put parentheses around it so you don't forget to distribute that negative sign to the terms other than just the first one. For now, I don't want to add these two together. I'm just going to try and keep them separate. When you plug in 5, you should get 500 over 3. So after evaluating the two separate intervals, you should get 500 over 3 and negative 136 over 3. So these values are what we had expected, which is that first one we expected to be positive and the second one we expected to be negative. Our last step is to put these together to find the area. And to do that, we're going to do 500 over 3, but then we're going to add, because we're changing the negative 136 over 3 to positive 136 over 3. The answer for this problem is 212 square units.